This CERTA project examined the potential for destruction of per and polyfluoroalkyl substances, otherwise referred to as PFAS, present in investigation-derived wastes, or IDW for short, through the application of hydrothermal treatment. Hydrothermal treatment involves the heating of liquid water in a sealed vessel to temperatures above the standard boiling point, which results in elevated pressure that keeps water in its liquid state. As water is heated to hydrothermal conditions, most often 200 to 350 degrees Celsius, the solvent properties are altered in a way that creates a uniquely reactive environment that can catalyze many reactions like those that degrade PFAS. These changes are being exploited by the nascent biofuel industry to promote conversion of biomass like algae into liquid and gaseous fuels. In this project, we set out to investigate whether the same conditions might be used to promote treatment and destruction of PFAS-contaminated water and sediments. For our first task, we screened a wide range of potential chemical amendments for their potential to promote degradation and defluorination of perfluorooctane sulfonate, or PFOS, one of the most problematic PFAS. We tested a range of acids, bases, oxidizing and reducing agents, as well as metal nanoparticles. Results from these tests showed that several reagents, most notably sodium hydroxide, a low-cost alkali base, were effective in promoting PFOS degradation and defluorination at 350 degrees. Detailed follow-up experiments showed that rates of sodium hydroxide catalyzed PFOS degradation increased with increasing base concentration and temperature. Tests with a related PFAS, perfluorooctanoic acid, or PFOA, showed that this chemical was even more reactive than PFOS. For our next objective, we tested whether sodium hydroxide would also promote destruction and defluorination of a much more diverse group of PFASs that have been identified by high-resolution mass spectrometry methods in aqueous film-forming foam, or AFFF for short. These AFFF are used in fire training activities and have been implicated as a major source of PFAS contamination in groundwater supplies. We were able to identify many PFAS structures, and our test showed that every one of these structures was destroyed by application of hydrothermal conditions together with sodium hydroxide amendment. Measurements of inorganic fluoride ion release also confirmed that fluorine originally present in the PFAS chemical structures, that is where the fluorine is bonded to organic carbon atoms, were released as fluoride ion, a substance that drinking water utilities commonly add to water supplies for dental protection. We also conducted tests that showed that several common co-contaminants of PFAS detected at fire training areas, including chlorinated solvents and hydrocarbon fuel contaminants, were also destroyed. Finally, as a proof of concept, we applied alkaline hydrothermal treatment process to some investigation-derived waste samples and some PFAS-contaminated soil samples that were collected from the Department of Defense facilities. Analyses of these samples showed high levels of many PFASs of concern, including PFOS and PFOA. After treatment, though, at 350 degrees with sodium hydroxide, more than 99% of most of these chemicals were degraded. So in summary, this project introduces a potentially promising new technology for managing PFAS wastes where high levels of destruction can be achieved. Destruction, not just removal, is important when managing PFAS waste to ensure that the environment is protected and liabilities are eliminated. Estimates of energy requirements for these processes indicated that it is much more energy efficient than incineration of the same liquid streams. So the technology has promise as a potential on-site treatment to address IDW as well as other liquid concentrate streams, even unused AFFF stockpiles. And the project team is currently conducting research to translate this technology into an economical and sustainable treatment system.